And I should point out, since Bob is here, I'm also co-author on, well, the original version was the Jurassic Park Institute Dinosaur Field Guide, and the current updated version is the Jurassic World Dinosaur Field Guide, available on Amazon. So, among other things. So, yeah, so I'm here to talk about carnivorous dinosaurs. That's a surprise. No, I work on carnivorous dinosaurs. They're my babies. Oh, and by the way, are you guys streaming now?
Yes.
Hi, Cam.
Although you're all dark now, but that's
Am I? Okay, yes.
Yes, he's watching. He's
okay.
watching.
Hi, Cam. There we go. Okay, so I may actually. Good. That'll work better. Okay, so I work on carnivorous dinosaurs in general. I work on Tyrannosaurus in particular. Here's part of the growth series of Tyrannosaurus on display at the LA County Museum. And of course, carnivorous dinosaurs are well known to the public. They've been the stars / villains of movies for generations upon generations. But of course, they're more than that. Just, you don't have to be scared of them. Actually, it's the internet. It's cats and dinosaurs. So there's a lot we can learn about them still. They're an important area of research, and they go back to, in terms of research on them, they go back to the very first days of dinosaur paleontology. So the first fossil carnivorous dinosaur was the first fossil dinosaur recognized by science, discovered by this guy, Reverend William Buckland, who was a geologist at Oxford in the early days of the 1800s, where in England, in the area around Oxford, discovered over the course of several years the bits and pieces of a carnivorous dinosaur. Now, here's the mount of the specimens at Oxford Museum, where he used to teach. I always thought this is kind of an odd mount. Literally, they have its head where its butt goes. Because there's a skull, and there's the hips, and that's the butt edge of the hips. But, hey, I didn't put this together. So, and in fact, what was initially found was this lower jaw. And that piece showed that it was a reptile, but it had very large blade-like teeth, similar to monitor lizards today, things like the Komodo dragon and the Nile monitor, which are carnivorous creatures. So they recognized it as being a large carnivorous lizard-like animal, to which Buckland gave the extraordinarily uncreative name, Megalosaurus, big lizard. That's what it means. It was the early days of paleontology. The names were not particularly creative. The first two fossil mammals from the early part of the Cenozoic, well, one of them was Paleotherium, or old animal. And there was also from South America, Megatherium, big animal. So, yeah, Megalosaurus, named in 1824. And they had just enough to know that it was something weird. But they didn't have very much. So they had hip bones, which they actually recognized as hip bones. They had leg bones, which they recognized as leg bones. And one of the unusual things about that is that the leg was oriented directly up and down. They could tell by how that thigh bone fits into the hip. It's not sprawling out to the side as in modern lizards. So Buckland pictured it as sort of a bear-like lizard. Oops, wrong way. And in fact, Megalosaurus was one of the stars of the original Jurassic Park. The original attempt to reconstruct and bring dinosaurs back to life. It was just 2 years after, 12 years after Dinosauria was named, the group of fossil animals that we call dinosaurs. And Sir Richard Owen, the director of the British Museum of Natural History, wanted to put full-sized restorations of dinosaurs and other fossil animals as currently known on display as part of the Crystal Palace exposition. And here were the initial drawings by Benjamin Waterhouse Hawkins. And here is Waterhouse Hawkins' lab, where we see, here's the front end of Iguanodon, the butt of Hylaeosaurus, an armored dinosaur. Hey, it's Paleotherium. And a couple horribly misinterpreted Permian and Triassic animals. And those specimens are still on display. And there is Megalosaurus over there, hulking and lurking in the presence of the herbivorous dinosaurs, Iguanodon and Hylaeosaurus. And actually, these are the original 3 dinosaurs. In 1842, Sir Richard Owen coined the word Dinosauria in the context of these 3 creatures. And he recognized that there were these animals, these reptiles from the Mesozoic era that were distinct from all living reptiles by a number of anatomical features, including that upright stance of the legs, and also their tremendous size. And that's why he deemed it appropriate to call them Dinosauria, fearfully great reptiles. But none of these were based on really good specimens. And so there wasn't a real good idea exactly how these creatures were shaped. That would eventually change. Some of the first evidence that Megalosaurus and other carnivorous dinosaurs have been interpreted in an extremely wrong way came from far-off New Jersey. Discoveries described by Edward Drinker Cope, and right there, not terribly far away, is the quarry where the original specimens of a North American carnivorous dinosaur were found. They included, here is a finger, and including its claw, it's the thumb. Other parts were discovered. There's the upper arm bones, both right and left. And take a look at that scale and compare that to the shin, and that's the same scale. And from this evidence, Cope was able to recognize that this creature had very different proportions than sort of a bear-like lizard, that it had very short arm bones and very long leg bones. And so carnivorous dinosaurs were beginning to take shape. And so that actually wasn't too bad a restoration given the limited material at the time. Oops, hang on. Keep on hitting the roller by accident. This creature was initially called Laelaps by Cope. Laelaps is a dog from Greek mythology that was turned to stone while leaping in midair. And so that's kind of a poetic name for the fossils of a petrified creature with long legs. But unfortunately, there already was, I believe, an arthropod, a bug, that had the name Laelaps, and so it had to get a new name. And it was given a new name by Cope's great rival, O.C. Marsh, where he called it Dryptosaurus, the wounding reptile, or wounding lizard. So our first good evidence that carnivorous dinosaurs had a body shape very different than what previously thought. And it was temporarily on display in the old days. Here is a reconstruction, or the construction facility, the preparation lab facility at the Academy of Natural Sciences, where we've got Hadrosaurus, the duckbill, which was known for more material, although by no means that complete. And little bits of Dryptosaurus were mounted. So they had casts of the arms, and they had reflected right and left the legs. And that would have been the first the first carnivorous dinosaur mount, but I am not certain this ever actually went entirely on display. There's this one photograph of it that was published by Ken Carpenter a couple decades ago, and I don't think there was any record of it going on display, so kind of a shame. But what did get on display was this painting where we've got Hadrosaurus, the original discovered duckbill, and a bunch of Laelaps or Dryptosaurus attacking them, and it's kind of scarily, creepily human in its own way in this restoration, but still closer than the original ideas of by Megalosaurus. What's even more impressive is that this painting is by Benjamin Waterhouse Hawkins, the guy who had also done that great big galumphing version of Megalosaurus. And it shows that within his own lifetime, the ideas behind carnivorous dinosaurs had radically changed. But we finally, by the later 1800s, actually had good skeletons of carnivorous dinosaurs, both small and medium-sized. So on the small scale, we've got little Compsognathus, and from Germany, the Jurassic Germany, and from a slightly older, but not much older, but from the American West, Ceratosaurus, the first relatively complete carnivorous dinosaur of moderate-sized skeleton, formerly on display at the Smithsonian. It is currently off display because they're redoing the entire paleo halls. It will be back on display, and I believe it's going to be free-mounted finally. It's spent most of the last 100 years encased, half of its skeleton encased in a wall, which makes it A, bad for people who just want to look around and see the specimen, and B, bad for researchers who want to know what like the left side of the animal looks like. But of course, we now know a lot more about carnivorous dinosaurs as more and more specimens were found. So from early in the last century, the famous AMNH 5027, the famous T-Rex mount at the American Museum, the poster child of Jurassic Park. They specifically used that silhouette for the logo of Jurassic Park. So, what are the carnivorous dinosaurs? Well, carnivorous dinosaurs, technically, the name of the group is Theropoda, which means beast foot, for no really good reason. Because their feet don't look particularly beastly. I mean, they have nice big claws, and I suppose that's what O.C. Marsh, who coined the name, was going after. Ornithopoda, bird foot, would have been a lot better. He actually used Ornithopoda for a different group of dinosaurs, only they don't have very bird-like feet. But, you know, both those names are better than Sauropoda, the long-necked guys whose feet are absolutely entirely unlike the feet of lizards. So, yeah, I don't know what Marsh was thinking. So this was, up until this week, the preferred hypothesis of where carnivorous dinosaurs go. So there's this branch over here. As the close relatives of the long-necked plant eaters, the sauropodomorphs, so that the basal split between dinosaurs were the lizard-hipped dinosaurs, the saurischians, and the bird-hipped dinosaurs, the ornithischians, that include duckbills and armored dinosaurs and horned dinosaurs and so forth. But Wednesday, a paper came out that sort of has offered a radically different hypothesis of the relationships among dinosaurs. It is still being discussed and will be discussed for a while in paleontological circles, so don't say this has been demonstrated to be the truth. However, in looking at their study, I cannot see anything that they've done that is clearly wrong. So we can't outright reject it, and there is a lot of good data in there. So what is this new hypothesis? Well, here's the paper. So Matt Barron, a graduate student, his advisor, Paul Barrett, and Paul Barrett's advisor, although to be fair, he is also Matt's advisor as well, Dave Norman. So 3 generations of dinosaur paleontologists who know what they're doing, these are no slouches, came up with this radical new hypothesis where, again, this is the long, complicated version. Let's do it a easier version. Here's the traditional model with the long-necked form, sauropodomorphs, as closer to theropods than they are to the bird-hipped dinosaurs. And that grouping of the sauropodomorphs, the long necks, and the theropods together are the saurischians or lizard-hipped dinosaurs. But the new hypothesis shifts these two groups around. So, if you enjoy that, you'll see it again. There we go. Okay, so I accidentally duplicated something there. So we now have a grouping of the bird-hipped dinosaurs and the carnivorous dinosaurs, collectively called Ornithoscelida, which is an old name, a synonym for Dinosauria, actually. This is the new 2017 model. Whether this was going to withstand additional scrutiny, we'll see. It's certainly something to consider. But really, I'm not so much interested in that, at least not for this talk here. I want to talk about carnivorous dinosaurs, what we know about their anatomy, what we can infer about their biology, and some of the interesting things that they did in their time here on Earth. Carnivorous dinosaurs went through tremendous differences in size. So I love this illustration, this photograph taken by Larry Whitmer and his students. Here's the skull of Tyrannosaurus, and tucked into one of the foramina, one of the openings in one of the bones, the skull of Archaeopteryx. So giving you a sense of the size range of Mesozoic carnivorous dinosaurs. They've also done one where we see the entire size range of carnivorous dinosaurs, but that spoils the punchline, although using Archie here is kind of spoiling the punchline here. Where they show the very smallest skeleton of a member of the Theropoda next to an individual tooth of Tyrannosaurus, and the individual tooth of Tyrannosaurus is greatly larger. So, carnivorous dinosaurs, theropods, actually in some ways are the least transformed of the dinosaurs, in that all dinosaurs started off as bipedal animals, animals that walked on their hind legs, and their forelimbs were modified for grasping and clutching. And carnivorous dinosaurs, theropods, kept that body plan throughout their history. Occasionally they modified their front legs into something else, but as far as we can tell, they never modify them back into legs. Whereas in the other groups of dinosaurs, they always, at some point, turn back into legs. So this basic shape of a two-legged strider with grasping hands, sort of a longish neck and a skull full of pointy teeth, describes a lot of the diversity of carnivorous dinosaurs. So we can start here with a primitive form like Tawa from the Triassic. And although these things vary greatly in size, and they vary greatly in diet, and in some cases in forms of locomotion, they still keep that same basic pattern throughout. And it makes them, in some ways, interesting to study in terms of issues like locomotion, because it's that same basic engine, that same basic drive, slightly modified, rather than something radically transformed, like from a small biped into a stegosaurus or a triceratops, where we have to deal with four limbs and different gaits in the front limb and hind limb and so forth. Although we will see that there is one branch, at least one branch of the theropods that actually do something very different in locomotion eventually, and that is take off into the air. Now, some carnivorous dinosaurs are, of course, very, very, very large. Dinosaurs are famous for producing very large forms, so that is a meter bar at the bottom, and this is an illustration of the largest specimens of the largest genera of dinosaurs scaled to each other. So good old Tyrannosaurus rex is the largest one for which we have good, complete skeletons of a large individual. There are convincing large individuals of Spinosaurus that do strongly suggest it is longer than Tyrannosaurus. May not be more massive. There are a few forms which might or might not be more massive that are known for much more fragmentary specimens, and then a lot of ones that are a lot smaller. One thing it does turn out, though, is that the large-bodied carnivorous dinosaurs sort of max out around the same body size, and that's probably about as big as you can be and be an effective meat eater. We don't see radically different sizes because these are occurring independently. So this would be one reaching that body size. These guys would be an independent version. This would be an independent version, all reaching that same general body size. The paleoartist and researcher Scott Hartman did an attempt to try to reconstruct the masses of the largest individuals of Giganotosaurus, a giant southern predator, and Tyrannosaurus rex, and in his study, T-Rex taps out slightly more massive. He calculated a mass of about 8.4 tons, compared to 8.2 tons for the largest Giganotosaurus. That's only 200 kilograms difference, which to you and me would be a lot, but to them is one meal. So basically that's saying that these guys are the same size, effectively the same size, especially given the very small sample size. There's no reason to think that one is demonstrably larger than the other. But all the biggest carnivorous dinosaurs are dwarfed by the biggest herbivores who achieve tremendous size. And basically, depending upon how you estimate the mass, they get up in there 60, 80, 100 tons. The mass of a herd of elephants, so much, 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 much larger than any of the carnivorous dinosaurs. But they're little guys too. Not all carnivorous dinosaurs are giants. Here's Sinosauropteryx. We'll get back to him eventually. This is the first non-bird carnivorous dinosaur that demonstrated something on the body other than scales. It's a little guy. It is much larger, though, than little Epidendrosaurus, although, to be fair, we don't know Epidendrosaurus is full-grown. Those are centimeters, and 2.5 centimeters is an inch, so that's a 2-inch scale. Total, this is an animal that could stand on the palm of your hand and you wouldn't feel it, or you wouldn't feel it very well. So they're very tiny ones as well. So in terms of how they were meat eaters, and they're carnivorous dinosaurs, how were they meat eaters? Well, they've got these blade-like teeth, at least ancestrally, very good for slicing stuff up. They've got pretty nasty jaws. They've got relatively powerful claws, so between the three of those things, those are nice stuff to grab onto a prey item, like Stegosaurus with. The majority of the carnivorous dinosaurs really do have blade-like serrated teeth. I mean, they're narrow from side to side, they're long from front to back. About half the total length of the tooth is rooted in the jaw, the other half sticks up out of the gum. And most people don't appreciate that if you don't look at the skeletons. If all you look at are like movies or toys or models, you often have a sense that carnivorous dinosaurs are sort of round snouts like an alligator, but they don't. They're very, very flat sides to the skull, sort of hatchet-shaped, very narrow skulls. And it turns out the majority of them don't even have a solid bony palate. So in fact, they're not much like the jaws of an alligator or a wolf, something adapted to bite and hold on for periods of time and really struggle with the prey with. They're slicers, they're hackers. They're not grab and crush jaws. That describes most of the carnivorous dinosaurs, but it doesn't describe all of them. That's sort of the baseline. But from that, we see a lot of variation coming off. So one particular branch that goes off in its own direction are the Spinosaurs. So here's Suchomimus, one of the members of the Spinosaurids. And you can see they've got these very long, slender snouts, very compressed from side to side, but much more solidly built than the snouts of, say, an Allosaurus or an Acacanthosaurus. They still have those powerful grasping arms, very, very large claws, actually. And here's a nice little animation with a reconstructed skull of the largest and last of the Spinosaurus, well, largest at least, of the Spinosaurids, Spinosaurus. And you can see it's, in some ways, it's very much a carnivorous dinosaur trying to be a crocodile. There's a lot of convergent adaptations to them, including moving the nostrils way back up on the snout, and also including having teeth that are conical. They're shaped like cones. They're not blade-like at all. Additionally, we have the gut contents of some Spinosaurids, and they include both the bones of land-dwelling dinosaurs and very large-bodied fish. And in fact, all the specimens of Spinosaurids found so far are in environments that were estuarine or bay environments or coastal environments in which we find very large-bodied fish. And it seems like the suite of adaptations that we see in Spinosaurids is that they're able to sample parts of the ecosystem that a typical meat eater wasn't able to, and that is to get after the fish as well as the land animals. So the idea that these guys may have been, in some ways, kind of like grizzlies, only the salmon run is year-round. So able to get in there and get big fish out of the water to munch on, as well as going after land dinosaurs and other land animals as well. You know, a diet in some ways very similar to something like a Nile crocodile. A Nile crocodile eats a lot of turtles, it eats a lot of fish, it eats a lot of antelope, it eats a lot of people who might be unfortunately walking by where the crocodiles are. And the same sort of thing here. They may have been eating both land and aquatic stuff as well. In fact, there is the suggestion based on some recent specimens of Spinosaurus found that that particular genus, that particular member of the group, may have been even more aquatic than the others. It may have spent a lot of its time in the water. Some of the evidence does point that way. Unlike most carnivorous dinosaurs, its bones are very solid. It doesn't have a hollow cavity, or doesn't have much of a hollow cavity in it. However, we don't have a really complete skeleton of Spinosaurus yet, so the exact proportions of the body are still a matter of debate. So, that's one direction off of the main body plan that carnivorous dinosaurs went. Another direction, far more famous direction, of course, are the Tyrannosaurs. There's the last and largest of the Tyrannosaurs, Tyrannosaurus rex itself. This is actually the specimen for which the name Tyrannosaurus rex was coined. So on display at the Carnegie in Pittsburgh. Tyrannosaurs are infamous for having these dinky little arms, and yes, it's true they couldn't reach their teeth with it. They could barely touch fingers, maybe. They might have been able to scratch their chest, but that's about it. They were not really that useful. However, you know, sure, everyone makes these damn jokes about Tyrannosaurus arms being useless, but I'm sure they would say the same things about our jaws. And that actually kind of gets the point across. If you've got jaws like a Tyrannosaurid, you do not need arms. So what were the arms for? Staying out of the way of the jaws, basically. That's what they were there for. They had Tyrannosaurids lasted a couple more millions of years, the arms would probably have gone the way that the wings of kiwis had gone, which is to tiny little stumps. Because Tyrannosaurs, unlike most carnivorous dinosaurs, actually have these rounded snouts up front. And they have reinforced inside of the mouth. They actually have the jaw bones on each side meet at the front of the snout, unlike most carnivorous dinosaurs. And their nasal bones, the top of their snout, is all fused together. And their teeth, I thought I had pictures of the teeth. That's okay. The teeth of Tyrannosaurs are different in form. They are not blade-like. So every single documentary or kids' book says Tyrannosaurus rex had a teeth full of steak knives. If you try to use a Tyrannosaurus tooth as a steak knife, you will go starving because you cannot cut meat with a Tyrannosaurus tooth. It is round in cross-section. And about 2/3 of its length is in the jaw. So these are piercing and crushing and smashing teeth. They are not slashing teeth. And so Tyrannosaurids, unlike most of the carnivorous dinosaurs, seem to have had a very strong bite. And a bite where they could clamp down on prey items and twist and turn and yank off muscle and flesh and bone. And we actually have specimens of plant eaters from the age of the Tyrannosaurs that actually have smashed bones that they've actually healed from. So we do know that on occasion, Tyrannosaurus would go after them and smash apart the bones by clamping onto them, and the herbivore got away. We also have Tyrannosaurus poop, and in the Tyrannosaurus coprolites, there are these smashed fragments of plant-eating dinosaur bones. So they did go all the way into the bone while feeding, at least on occasion, which doesn't seem to be the case with most other carnivorous dinosaurs. But not all the scary carnivores are giants. There are small, scary forms as well. This is a raptor dinosaur. We're talking about dromaeosaurids or raptors. There's this wonderful new specimen of Saurornitholestes that's being described by Phil Curry and other researchers right now. They are not normally this good. This is really rare. And of course, famous in the raptor dinosaurs is that sickle claw on the toe. First discovered or first recognized in the foot of Deinonychus, found by John Ostrom of Yale in the 1960s. And at the Academy downtown, there's two specimens of Deinonychus going after its traditional prey, Tenontosaurus. Poor Tenontosaurus, this plant-eating dinosaur that almost every illustration in existence of it is it getting attacked by Deinonychus. You know, it had a life. It did stuff other than be meat, but it makes it more interesting. So this big slashing claw is flat from side to side. It's blade-like, and it's on a retractable claw. It's on a retractable toe. It's very much like the toe of a big cat, whereas as a cat has all of its toes as retractable. In the case of dromaeosaurs, of raptors, it's just this digit 2 that's retractable. And when Ostrom found this claw and this foot, he suggested it was used as a predatory weapon. It was used to go after the throat or the belly of a herbivorous dinosaur. But it's always nice to have specimens that back that up. And so a few years later in Mongolia, this wonderful specimen was found where we've got a velociraptor apparently interlocked with a small horned dinosaur, Protoceratops. So just to orient you, there's the nose of the velociraptor, that's the back of its head. Its neck is pulled back in an S shape. Dinosaurs can pull their necks back into that sort of S shape. There's the back, there's the tail. So here's the Protoceratops, the triangular head. The top of it is eroded away. That's actually how they found the specimen, is that was sticking out of the rock. Here is the backbone, there are the tops of the hips. And here's the left arm of the velociraptor grabbing onto the face. The right arm is somewhere down near the mouth, and we'll see exactly what's going on. The right leg of the velociraptor was found underneath, well, it would have been pinned to the ground at the time, but that left leg, you know, it's sticking off towards the vulnerable part of the Protoceratops. So after the specimen was prepared out, and now I've rotated the picture 90 degrees, so we're looking at it from the side. So here's the Protoceratops. The skull is cleaned off by erosion. There's the back of the velociraptor. the left arm is grabbing onto the face. The right arm was trapped in the jaws of the Protoceratops. It's this right way in there. The right leg of the Velociraptor is trapped under its body. With the left leg, there's the thigh, the knee, the shin, the ankle, the foot, and there's that sickle claw inside the neck of the Protoceratops. I mean, it's inside the neck. Those are the neck bones. All the good stuff is below the bones, the windpipe, the jugular vein, the esophagus. And that's just the bony part of the claw. That would have had a sheath on it. Maybe 20%, maybe 50%, maybe more, longer. So this Velociraptor was found in the midst of its claw inside the throat of the Velociraptor, sort of tearing stuff apart. Of course, the Protoceratops, even if it had been killed by the claw, would have taken the arm of the Velociraptor right off, because horned dinosaurs had probably the best shearing bite that nature has ever evolved. And of course, the nearest vet is 80 million years away. So they both would have died regardless. Thankful for us, not so much for them, the sand dune upon which they were on seems to have collapsed because of the fight and preserved them in this moment of combat. Now, we don't know that the raptor claw is always used quite so dramatically. That happened to be a rather dramatic use. And it's been suggested its more common use would be something similar to what we see predatory birds using it as. This has been called the raptor prey restraint, or probably ripper hypothesis. And the idea is it being used to help subdue the prey while the front arms and the beak or the jaws try to tear it apart. And there are still animals today that do this sort of attack, and those are indeed the modern raptors. Doesn't always work, at least not right away. So here is a modern Galapagos hawk going after a marine iguana. It's going for a ride, but eventually the marine iguana does weaken and the hawk is able to kill it. Yeah. But not all the carnivorous dinosaurs stayed that way. So while it's true, lots and lots and lots of the carnivorous dinosaurs did have some form of blade-like or otherwise meat dealing with teeth, a few branches of the carnivorous dinosaurs went in other directions and became plant eaters. Here's a little Chilesaurus, recently described, shown actually about life size as projected. It's not a big animal. And those are its teeth, and those are not the teeth of a meat eater. So this is something that's eating sort of tough vegetation. There are others who decided teeth schmeeth, we're getting rid of them altogether. So here's the ostrich-like Ornithomimus, and here's a beautiful skull of one and totally toothless, covered with a keratinous beak. We don't actually have that much in terms of the gut contents of the ostrich dinosaurs, but given their overall morphology, an ostrich is probably not that bad a model. And ostriches today are omnivores. They eat plants, they eat eggs, they eat small-bodied animals, whether they're arthropods, bugs, or small vertebrates or whatever. And Ornithomimus would seem to have been a reasonable feeder on those sorts of things. There are some toothless dinosaurs with more heavily constructed skulls that may have been eating something a little tougher on occasion. These are the Oviraptorosaurs. So here's the skull of one called Rinchenia. It's a rather weird-looking thing. Just to orient you, that's the jaw joint. That's the front of the beak. It has this enormous crest on its head. That's the eyeball right there. Well, the eyeball will go right here. And here is a North American cousin of it, Anzu. This is the specimen on display at the Carnegie in Pittsburgh. And art by Bob Walters in the background. So, and I'm actually working on a new specimen of Anzu that we found out in southeastern Montana with the folks at the Burtby Museum in Rockford, Illinois. And these guys, we have the gut contents of some Oviraptorosaurs that do include small-bodied vertebrates. They include lizards. But these are another group that looks like a broad diet that includes both plants and meat is quite reasonable. And in fact, the most primitive Oviraptorosaurs have teeth that look like an iguana lizard, which modern iguanas are indeed omnivores. And then there are things like the Therizinosaurs. Here's the skull of Erlikosaurus, the best skull of a Therizinosaur so far, which has a toothless beak in front, and then leaf-shaped teeth behind. It almost certainly was a herbivore. In terms of the body, The Therizinosaurs are sort of beer belly dinosaurs. They have very, very round bodies. They have large guts and very short feet for a carnivorous dinosaur because they're not carnivores anymore, and you don't have to run down grass. Well, not that grass is on their diet necessarily, but other plants. They did tend to have very nasty, sharp-looking claws, but nasty, sharp-looking claws are not unique to carnivores. There are plenty of insect eaters that have them, and of course sloths, including the giant ground sloths, had large, sharp claws. And in fact, in many ways, these guys may have been the dinosaurian equivalent of the giant ground sloths. The last and largest of the Therizinosaurs was Therizinosaurus itself. This is shown much smaller than life size. It is a tremendously huge animal. Unfortunately, we do not have that much of its skeleton yet, but we have enough to recognize it's a Therizinosaur, and this, as projected, is about life size. So it's got sort of Freddy Krueger-like claws on its hands. And here's an illustration by Louis Ray of one feature that those claws might be useful for. I mean, they probably were useful in acquiring food, but if you are a big pot-bellied dinosaur in a world with tyrannosaurs, being able to defend yourself when you can't run and you don't have armor is probably a good thing. So yes, there are some of the meat-eating dinosaurs who decided they weren't having any of it. They went over to herbivory, and yet, despite the very cruel father tyrannosaur here, they actually do remain carnivorous dinosaurs even when they stop being carnivores. So in other words, they stay as part of Theropoda even if they aren't eating meat. Now, so that's the fierce part. I'm going to briefly talk about the fast, and then I'll get to the feathered stuff. It's been noticed for a long time that when you look at the general limb proportions of the carnivorous dinosaurs, they tend to be a lot more long and slender than those of the herbivores from the same time period. So we can compare, Allosaurus to its contemporary Stegosaurus, or Tyrannosaurus to Triceratops. And overall, when we look at the legs of a striding animal, the longer the tibia or shin bone is, and the longer the metatarsus or foot bones are, the more rapidly moving the animal is. That is, you're covering more distance with each stride, and distance over time is speed. So, comparing these two, Altosaurus with its stubby legs is a Therizinosaur, probably much, much slower than the young Tyrannosaurus here. This is Jane, the young Tyrannosaurus. And in fact, when we plot out the data, this is the length of the femur versus the length of the foot, the metatarsus. In blue are the theropods, and they consistently have much longer feet than do the herbivores, in red for bipedal ones and in green for quadrupedal ones. That doesn't mean that a big T-Rex could outrun a Jeep or a racehorse. It doesn't have to. You don't have to be a super athlete if what you're chasing isn't a super athlete. All you have to do is be faster than the stuff you're going after. And it looks like consistently the carnivorous dinosaurs were more agile, faster moving than most of the large-bodied herbivores of their environment. It's true, though, that some groups seem to have been more speed specialists. So if you look at a typical carnivorous dinosaur, there's Allosaurus' foot standing in for that. And these are the long bones of the foot, and that middle bone is about the same length from top to bottom. And it's about the same width from top to bottom, not the same width as the two bones on the side. This is sort of the starting point for an average carnivorous dinosaur. And we do see that two different plans sort of branch off from that, both of which might be associated with both of us may be associated with faster moving speeds because they're always associated with longer limb bones. One is what we see in tyrannosaurs and ostrich dinosaurs, where that middle bone gets pinched in between the two of the other bones. The other one shows up in several of a group called the ceratosaurs, where it's the opposite pattern. The middle bone remains the thicker one, and the two side bones get narrower and narrower. In some ways, it's very similar to what happened in horse evolution. And in both cases are associated with very long metatarsi, long foot bones, and long tibiae. So it could be that the forms that evolved these adaptations were becoming more rapidly moving than their kin. And here's just a Tyrannosaurus, a young Gorgosaurus to show an example of such a dinosaur. Now, when Deinonychus, the first raptor whose foot claw was discovered, John Ostrom did make a lot of observations on how similar the skeleton of Deinonychus was to early birds, to Archaeopteryx. And in fact, when Ostrom came across, by accident, he didn't even know it was an Archaeopteryx, a specimen of Archaeopteryx that had been misclassified as a pterodactyl, he really was struck by how similar the arm anatomy was between these two. And he started looking at the rest of the anatomy and realized that, yes, carnivorous dinosaurs and early birds were extremely similar, and he resurrected an old idea from the 19th century that had been forgotten for the most part. And that is that birds may have arisen from the carnivorous dinosaurs, from the theropods. Now, we have especially seen in the last 2 decades an explosion in our understanding of Mesozoic birds, of birds that were contemporary of the dinosaurs, especially the other dinosaurs. And we now see just a gradient that goes from creatures that everyone agrees are dinosaurs to things that everyone agrees are birds. There is no single major jump in discontinuity. It's a continual gradation. These are various of the steps along the way. Everything I've shown so far, well, actually not the previous one, all the rest of them have teeth. And birds retained teeth almost up until the origin of modern birds, although a few groups independently lost them. So there is no distinction between being a bird and being a dinosaur. You're a bird, but a bird is just a type of dinosaur, just the way a stegosaur is a type of dinosaur, or a sauropod is a type of dinosaur. And that's just looking at the skeletal anatomy, but there's other stuff going on. So there's this continual gradation in the history and the rise of birds, and there isn't a single spot where you say, this thing is unquestionably birdie versus not birdie. So in my veins flow the blood of dinosaurs. Dinosaurs, I tell you. And yes, so it means that from the mighty, things that are somewhat less mighty have arisen. But that's nature for you. And most of those discoveries were made independent of our knowledge of what's on the outside of the creatures. But we have also discovered what's on the outside of the creatures. And starting in, and this is scary, more than 20 years ago now. That doesn't seem right, but it's true. We've now known that at least some of the carnivorous dinosaurs had stuff on the outside of their body other than scales. In fact, at the 1996 meeting of the Society of Vertebrate Paleontology, which was up in New York City, there's normally a mixer event before the main talks. And so I arrived, going around in the exhibit area, and Ken Carpenter, as paleontologist, came over to me and said, "You've got to go over to Phil Curry. He's got something really cool to show you." Okay, sure. Phil's a cool guy. I'm going to go see what it is. So he went up to Phil and he said, "Phil, I hear you have something to show you." He just had this enigmatic smile and he had a briefcase. And he set it down and he opened it up and he pulled out photograph after photograph of this specimen, where all over its body, some were close-ups, we could see it's not scales on it, but it's fuzz. And this was the first demonstration that something other than scales were present on the outside of carnivorous dinosaurs. Because this is not a bird, and this is not even close to a bird. This is a relatively primitive carnivorous dinosaur. And yet it's got fuzz on the body. And so, well, okay, maybe the stuff is actually, we say, homologous to feathers. It represents the same evolutionary origin. The reason we hadn't picked it up before is that it takes certain types of sedimentology to actually preserve these kind of tissues. Feathers are a very difficult thing to preserve, and what you really need is extremely fine-grained sediment in an environment that doesn't get disrupted by worms and other clams and other burrowing organisms. But it turns out there were some very large lakes in early Cretaceous China that were perfect. The sediment was derived from volcanic ash, so it's extremely, extremely fine. The bottom water was apparently very anoxic, so low in oxygen, worms couldn't live there. And so we actually have this stuff preserved. And first it was just things like Sinosauropteryx, and then other things started showing up like Oviraptorosaurs with actual honest-to-goodness feathers on the arms and tail. Some things with structures sort of intermediate, sort of long strap-like things coming off the tail. It's not just those ash feather-based beds, though. We now have other types of preservation showing phases of feather evolution that are distinctly not found in modern birds. So here is a chunk of amber described last year. And you can see, as some of the paleoentomologists said, hey, look, it's a well-preserved ant with a little bit of a theropod dinosaur in it. So yes, there's the ant. But here is part of the tail of a carnivorous dinosaur. That must have been really annoying to have this clump of amber on its tail. I don't know if the tail broke off or exactly what happened. We don't have the edges of it. So, and here is preserved on the inside the feather structure, and it's not quite like the feathers of any living bird. And the tail bones, what we can resolve of it, unfortunately the scans aren't really fine detail. We can't quite place where in the carnivorous dinosaurs it is, but it's well below the origin of birds in terms of its position. We have carnivorous dinosaurs with honest-to-goodness true feathers, like many, many specimens of Anchiornis. And since I was talking about spectacular preservation, this was presented last year at the Society of Vertebrate Paleontology and then described in a paper more recently using laser fluorescence and a technology that someone shoots laser at it and pictures come off. I'm not a laser fluorescence guy. I don't know how it works. Yeah, shoot lasers at it, and you get science. But it actually shows that as opposed to what we see in ordinary light, there's a lot of soft tissue structure preserved in at least some of these environments that can literally be illuminated with new techniques, including the soft tissue that was present, including the nodules on the skin and so forth. The little reticulated scales on the foot pads of a dinosaur. If you look at this in ordinary light, all you see is the bones. And you throw the laser on it, and you get this sort of stuff, which is really cool. And then fossil preparators around the world, they see this go, oh God, what have we done? Because who knows what we've destroyed by accident over the years. But who would have known, I don't think if O.C. Marsher's company had said, okay, someday we're going to shoot lasers on it, he should not have been a paleontologist, he should have been a physicist and get lots of money to having invented the laser in the 1800s. So, I'm sure right now, there's stuff going on that, in 50 years, those foolish people, they didn't use telepathy with the fossils. I know they're still alive. That's not true. So what would feathers be for in these sorts of animals? Well, in some cases, almost certainly for display. Lots and lots and lots of structures on the body are used for display. We know that at least some carnivorous dinosaurs directly brooded their eggs, and having a nice fuzzy covering can help keep those eggs warm. It might allow you to survive in environments that otherwise wouldn't be so good and healthy for creatures. So here's a reconstruction of a trudont in the snow. And although the Mesozoic was much warmer than today, there were parts of it that were cold. But at least some forms have really well-developed long feathers coming off of the arms and tail, and in some cases the legs as well, large enough that they're forming aerodynamic surfaces. And so this is not a bird, this is a raptor. This is closer to Velociraptor and Deinonychus than it is to, pigeons and chickens. And it's also not a big animal. So some of these early raptors were probably aerial to some extent. Nowhere near as good a flyer as a modern bird, but for that matter, Archaeopteryx wouldn't have been either. So these sort of flight seems to have been part of what some carnivorous dinosaurs did. Plus, now when we map out where we find these pennaceous feathers, these broad feathery feathers, it does seem to be restricted to mostly bird-like carnivorous dinosaurs. And so our new view of what things like Deinonychus and company would look like is a much more birdy sort of animal. So here's a new version, a new interpretation of Velociraptor, for instance. This is actually a Confuciusornis, but showing very, very broad feathers, but we see exactly the same feather structure in the raptor dinosaurs when we find them. So here's a reconstruction of a juvenile Deinonychus. And had those specimens in China been found first, long before the specimens in England, and been described by the scientific literature, we would have considered carnivorous dinosaurs to have been an early branch of primitive birds. We never would have labeled them as some sort of big bear-like lizard. And we wouldn't have to overcome this idea of them being lizard-like. Here's another interesting restoration of Velociraptor and ostrich dinosaurs here. And it's true that more simple feathery structure, proto-feathers or fuzz, whatever you want to call it, are more broadly distributed among carnivorous dinosaurs. And then a few years ago, something truly annoying happened. Because up until that point, it was only theropod dinosaurs that had fuzz. And that was okay. Okay, we could breathe. Okay, carnivorous dinosaurs, or at least some of them, are fuzzy or fuzzy ancestrally. And then some of the bird-hipped dinosaurs started to show up with fuzz. These are creatures closer to Stegosaurus and Triceratops than they are to chickens and ostriches and Tyrannosaurus and Velociraptor. And yet, they've got fuzz. They've got lots of stuff, actually. They've got scales and fuzz and little plates with branches coming off. They got lots of stuff on them that's not scales. Here's some of the fuzz coming off of it. Here are these weird little flat plates with the branches coming off. So, what do we do now? So we got fuzz over in the primitive members of the bird-hipped dinosaurs. We have fuzz in at least some groups of carnivorous dinosaurs. Is it all independent? It could be. It could be. Or it could be that the common ancestor of all dinosaurs was fuzzy, or at least had the capacity to make fuzz. And depending upon what branch you are, you may elaborate that more, or you may suppress it, or whatever. What I don't show here is that new hypothesis. If you move these guys over to the branch right here, then at least these guys, the sauropodomorphs, we don't have to deal with them being fuzzy. So, yes, it's not the way we picture dinosaurs normally, but at least some of them may have been more something along this line. So I do want to show, sort of end up with some surprises that are going on as well. So here is a little dinosaur, it's a Yi. Not only is it little, it has the shortest dinosaur name of all. Yi Shi, his last name is QI, so it's only 4 letters in its entire name. And it's a tiny dinosaur, but it has a weird long projection coming off one of the hands, which is, it is not a bone, it is a tendon or other structure which has become bone, ossified. It has become bone, but it's not a traditional bone. It is not like a metacarpal or a carpal or something of that nature. And at least some of that long structure seems to be associated with a membrane coming off of it. And so that has led describers to reconstruct it as sort of a bat-winged dinosaur, which is weird, because they're not supposed to do this. Even the flying one's supposed to fly with feathers and not flight membranes. So it's sort of a dragony, sort of thing. It's a little guy. It's the right side to be a glider. I like this one better because it still has the feathery fuzz on the body and so forth. And it shows that there are these weird surprises out there, that nature throughout the Mesozoic as today continues to experiment with different ways of being whatever creature you are. And it means there's all sorts of cool things to find still in the rock record. But sadly, 66 million years ago, rocks fell out of the sky, and it stopped being a world dominated by large-bodied carnivorous dinosaurs. One branch did survive, and it's birds, and it's one subgroup of the birds. It's the toothless birds that survived. But on the other hand, there are more species of birds than there are species of mammals, so at least by species count, they're winning. Although not by any other real count, because big mammals are the ones who are making up all the rules. So here, look at this creature. It's our legacy. Our legacy is throwing up a Doritos bag. So such is life. So again, dinosaurs, I tell you. So it's a very brief overview of carnivorous dinosaurs, but we're always going to be finding out new things, which is what makes it cool. So I thank you for your time, and I'll answer any questions if you have.